Hello. In the previous lecture, we considered combinatorial games, and we learned how to reduce these combinatorial games on graph. And for these graphs, we for any graph we learned how to make retrospective analysis that gives us understanding what game states are winnable and what game states are losing. And by the way, during this algorithm, we calculated counting function that gives us understanding how fast can we win or how slow can we lose. Okay, but what if the game is too big? For example, chess. There are too many states in this game, so we must we must come out how to evaluate possible chance of winning in some state. Okay, so we define new definition, game tree. A game tree is graph representing all possible games. It can be unfull for some game. It can be full. And for this game, in the same way for this game tree, in the same way we define these functions, this function, counting function, in the same way. So we need to understand how to estimate chances of winning in some state, if we in some state. So we define new function, heuristic function. It's a possible evaluation function is numerical characteristic of the game that depends only on the game state. Only on the game state. We don't calculate possible. We don't calculate this game state, this heuristic for some state, based on next states. This heuristic depends on current game state. Okay, and this is example of some characteristics. Some simple examples for chess. We can take sum of weights of one pieces, and for example sub weights of opponent pieces. Or in reverse, we can take number of disks equal numbers of opening disks, and for checkers in the same way. So okay, but how can we use it? How can we use this function in to find winning strategy that have best chances to win. We need to use Minimax algorithm and alpha beta pruning algorithm for it. We in the beginning of the algorithm, we calculate function for states that we can reach. For example, if there are 8 states, okay, it's fine. For example, we have 2 to the power of 16 states, 32 states, and we we can't calculate the next layer, and we stopped at 32 layer and calculate heuristics for every state. Okay, we calculate heuristics for every state, then we do what? We consider that the first player located in this position. In this states will be located second player, and so on. And for first player, we need to maximize our evaluation. For second player, we must to minimize chances of winning of the first player. So we just first player want to maximize it. Maximize it. Second player wants to minimize it. We take minimum for this, and so on, and so on. We take, and we find some strategy to win. Okay, and in the next layer, we can make this analysis. We can make this analysis one more time, but I make mistake. This will be no. That's fine. 2 to the okay, 2 to the power of 32. Yes. Okay. So that's it. We can make this analysis again and again for every state to calculate best strategy. That is not best strategy. We can make one more time in this state to increase our chances of winning. Okay, but if you consider, for example, chess, you can find out that this algorithm is too complex for chess. So we need to optimize it. We optimize it by alpha-beta pruning. For example, you can see that we have if we just I find it. For example, we already have calculated this graph, this subgraph. We start to calculate this. Okay, we climb out to leaves, and here we have that. Here we have 4, and here we have -3. Okay. 1 second. 1 second. I think about this. That's not a good example because we can make pruning in this situation, but we can do it in this situation. Okay, we reach, for example, 4. You can see that we have on previous layer we have 5 as maximum. here we have only 4, but the second player takes minimum, and if we meet something bigger than 4, the second player doesn't take it. So it's not necessary to climb out to some vertex if we meet some values that less or equal than value in previous layer. That's it. We just make this algorithm. Just if we meet that in previous layer, we get value that bigger or equal than value in next layer. We just prune this edge. For example, we have 6 for this. Oh, we have already 6 in this node. So we reach this leaf, then we return, and we get 5. 6 bigger than 5. That means we don't take to visit this edge, this subtree. Okay, you can see algorithm, I think. It's like you can see here algorithm, but if you implement it by yourself, it will be nice. It will be nice. So next, let's look at this more formally. Okay, we define alpha as the current maximum value of nodes score for maximization levels, and beta the current minimum value for the minimization level. Minimization level is the current level, and maximization level is a previous layer. Okay, now you see that we come out some optimization for our algorithm, and imagine that Deep Blue chess computer use this strategy to win Garry Kasparov. and now you can win any world champion in chess if you will program this algorithm. Okay. Next is Sprague Grundy theory, and why does it useful for us? Because in the previous lecture I considered NIM games, and I said that this NIM game will be discussed in the previous lecture, in the next lecture. So now we can win in this game. Now we can win in this game for complexity about ON multiplied by maximum pile in this piles. So we can decrease this complexity to ON, and we can reduce some combinatorial games to our new games. And we can calculate some games more efficiently. We can figure out how to calculate some games more efficiently using this theory. So we define what is direct sum of games. Non-formally, if we have two combinatorial games, these games represents as graphs with two states. Graph G1, we have two games, A and B, and G1, S1, B equals to G2, S2. And we have two initial states for these games, and we can play on this graph like choosing move. We move we move in the first graph, or we move in the second graph, and that's it. Так, 1 second. If I move, cannot. That's fine. Okay. And lose and win defines in the same way. If a move cannot be made in either of the two games, the one who has to make a move loses. And that's it. Okay, we define direct sum. I forgot to say that two games must be independent. Okay, operation of additional games. We have, I have already described this example, and notice that the operation is commutative because we can swap our games, and association and the operation is associative because we can imagine our game like one game, and that's it. Okay, and what? Okay, we have new game with multiple piles. It's direct sum of smaller games, E1, and so on. A6. Okay, we define neutral element in this theory. It will be just pair vertex in our definitions, in our previous definitions, just graph of one terminal vertex. And notice that if we consider some graph and this vertex, this will be the same that play only on graph, because we can make any move in this states in this state. So okay, consider symmetric strategy that we have already considered. Okay, if A is we'll consider only acyclic graphs, and notice if we consider in game, wait, I mean a game, a game, a plus a game. 1 second. Okay. In this example, I remembered that we will have already considered the strategy for table, and notice that if the first player start this game by some coin not in the center, it's placed not in the center, it we get symmetrical game, and this symmetrical game will he loses. In the second variant we have symmetrical game too, but he will be the second player in this game and he will win. Okay, just that's it. We just repeat symmetrical, we just reply symmetrical, and that's it in this game wait, the second player replies symmetrically to win in this game. Okay, define game outcome. What is it? It's just a value. Notice that, remember that game is graph and state. And the state can be n or p or d. And that's it. By the way, we have defined in the previous lecture d state differently. We define it like if game contains forever, we get that the state is d state. Okay, in this lecture we define d state like what? We have tic-tac-toe. In this tic-tac-toe we have tie, and we define tie like this. We have terminal states of the game, and we have tie states, tie terminal states, where no one wins. Okay. And equivalence. Okay, we define equivalence relation, Grundy equivalence. If we take any game, say C, and we consider this, and we get that this equality satisfies, we get that A is equivalent to B game. And notice that this is equivalent relation because if we have if a non-trivial, what transitivity is not trivial, if A game is equivalent to B game and B game is equivalent to C game, A game equivalent to C game. Why is it true? Because we can just transitivity A equivalent B, B equivalent C. It means A plus C, A plus X, or any X, we get this, And what we do, we just just we just make like this. We just fix this x and get this. That's it. Okay, next, convenience of some games. I forgot to write down it. Okay, if we have a game that equivalent to A1, A2 game, and B1 game that equivalent to B2 game, it means that A1 plus A2 game, A1 plus not A2, A1 plus B1 game equivalent to A2 plus B2 game. Consider this. Write down this as definitions plus C for every C. Okay, we can use associativity, I think, here, and this is any game, so we get that this game equivalent to this B1 plus C1, and that's it. Just make this equality using commutativity. Using commutativity, we make this. We make what? We make this. Сейчас нормально расписать. We can make this. You can using associativity and commutativity. Что сделал? C B1 plus A2 plus C. It's any game. It means we can replace this. So we get B2 plus A2 plus C. A2 plus B2 plus C. That's it. We prove it. We prove this, that this is this equals to this. Okay. Next theorem. For any losing game L and any games C, the equality V L plus C equals to V C satisfies. Okay, consider 3 cases. C game is N game, C game is P game, C game is D game. In the first variant we get that we have two games. L plus C, L and C game. In the L game we 1 second. In the L game we lose, that we get P, and in the N game we try to win if we make step. In this game that it doesn't make a sense because we get N for any, so we don't make any step. In the first situation we get that transform, нет, переводим, сейчас, move, сейчас, transform all game to PP game, and that means for second player we have it has for second player he has P game and P game, and whatever he make a move he loses. Okay, because if he have two P games and C games, unfortunately we get that now we are the first player is a second player, and that's it. Any game, any move goes to N, and second player answers symmetrically and wins the game. Okay, and in this otherwise we get D game. That C is D game. Okay, we can make induction once by steps count in L. We have graph, and we have terminal states in this graph. And suppose L game, suppose we have graph is now that we can make null steps. It's just a terminal vertex P, and that's it. We get equality. We get equality if our L game is just a null game, P game. Okay, and we have, suppose we have already prove that we have already just okay. Suppose A is P game, and for any game and any L game where first player loses faster, equality is already satisfied. Means we have some graph, and we prove that for if we locate it in some position, that more closer to terminal vertex, for example, we have X and Y state, and for Y state that closer to terminal vertex, we have already proved this. We suppose it, and okay, we suppose it, and notice that we have L and C game. In these games we must make move. If we move in L game, it doesn't make us any sense because we have LSP game, just LSP game, and we just переводим, как это, transform our game to N game. Okay, and that's okay, and we make step and it means we make step and in C game. It's D game. That is D game for the first player. And it games continues forever. Okay, that means we get that. No, что я сделал? Get this. This game continues forever because here we lose. Here we can lose. And here we make step forever. Make steps forever. Or lose. No, first player wants to tie game блин. Ничья важнее проигрыша для первого игрока. Поэтому он ходит бесконечно по графу. Так, next. Next, what is this? Equivalence of losers. Чего? Ладно. Okay, we have two corollaries. We prove this. L plus C is equals to C. For this is any losing game. This is any game. And we can apply these corollaries. For example, we have this. If A and B losing games, that means it equivalent to null game because no, because of this we are this equality and this equality. VB 1 second, think about this. We just add C to this and that's it. And C is at any game. C is any game. Okay, and second color is obvious too. We have that this is any game. Any game. Oh, wait. Нет. Any game. Lose game. And that's it. Okay. We have already proved that that A plus R a game is symmetrical game. In this symmetrical game we can the first player loses always using symmetric strategy. Okay, it means what? It means this plus C plus null equivalent to C plus null. It means commutativity. Using commutativity to prove that A plus L, A equivalent to star null. Okay, next let us denote the game nim with one pile of stones. Okay, here we have new definition. If we have nim game, and if we have stones in nim game, and there is only one pile, with this game we define like this on E stones. Okay, all of these games are winnable because we can just take all the stones. And notice that if we have If you have some different in games, with different in games are not equivalent, despite that these games are winnable. We just consider this quality. We we must to take some games that on games that we can't, this equality is not satisfies. Let e less than g, that means we can take from this pile, we can take g minus e stones and get g minus g minus e stones and get e stones. So it will be equals to e. We have two piles, two the same piles, and we have, and that means first player will win reply symmetrically. In this game, first player loses because the second player replies symmetrically. And we have here we have 1, here we have -1. We give an example of some game. On that we have inequality. That means e not equivalent to g. Star e not equivalent to star g. Okay, next lemma that will help us to prove general theorem. Game A is equivalent to game star E if only if when A plus star E is equivalent to star null. Okay, just use that we can that star null is equivalent to E plus E, star E plus star E, and we have that what we use associativity here. Here we use just that our assumption, and that's it. We have A that equals to star E, and we have the same here. Okay, now we have that any here we have I think what I think here we have that according our that we get that any nim game is star E are all classes of games on a cyclic graph. Star E that null to and so on, where E is from null to so and so on. I mean we can reduce some acyclic graph to some nim game. Okay, Sprague-Grundy theorem. Okay, let's define new function, Grundy function. Grundy function that denotes the number e such I is equal to star e. It means we have, once again, according to this we have that any game, this and this, any game is equivalent to some game on any game equivalent to some game on nim on a cyclic graph, and if from game A there exist moves to games A1 and so on and n, then we get that GA if we take minimum excluded function of all of game states, of all games with states we can make move. We get nim number for this game, for current game. This is a theorem. Okay, for example, we have Grundy number for Pithhoff game that we considered. Okay, it's obvious that null game is equivalent to null game on nim. Obvious that if we have here and here we have two piles that exist equivalent. Okay, and what is minimum excluded? By the way, if we take some numbers, if we A1 and so on, A2, we take minimum number for these numbers, and sub -1, we get minimum excluded of the set of numbers. For example, if we have null 5, 3, 4, max of these numbers will be equal to 2. Mix of these numbers, mix of these numbers, these numbers is equivalent to 4, and so on. Okay, we have for example, how to calculate for this state. We have now 1, 2, 3, 4, 5, and so on. We haven't 18, and according to this theorem, we will have 18 in this state. No, okay, we have, for example, 4. How can we get it? We take minimum exclude for this set, and this set, and take 4, and minimum excluded for this set will be 4, and that's it. Let's prove this theorem to prove that A is equivalent to some game on nim with these tones. It satisfies to show that A plus A star E is a Usain game according to our lemma. Where is it? Here's the previous lemma. Okay, we now we prove that A plus star E is losing game. Okay, we can make, the first player can make an A game step and star E game step. Okay, suppose it's make step in A game. No, the first player can make move in any of these games of A1, A2, and so on again. Suppose it can he make it to AG. She or he it make it to AG. Now the second player must move in the sum AG plus star E for some G. Okay, second player. We must prove that second player wins. Okay, but notice that E not equals to G. It means this game is losing game according to our proof. Where is it? This game is winnable, I think. According to what I proved. Where is that? Where is it? Oh, here. This game is winnable for second player, and we get that. And we get that second player wins, first player loses. Now let's prove it for star E game, if the first player might move in star E game. Okay. He make a move to some K, and notice that this K will be in the set because we take minimum excluded from our set, and that means all values that less than this value are less than this value if this value was greater than null. That means that means that means what? I'm trying to do not watch to prove. Okay, then the second player can make in A move to the game AG. Okay, and it can be win. It can win. Okay, that's it. The second player wins. Once again, we prove that for a game, first player loses. For a game, for the star E game, first player loses too, and that means a G plus star E is losing game, and it means that A equivalent to some game equivalent to game on nim. Okay, and I don't want to prove the theorem because I have no time for this theorem. This theorem is really big. Where is it? If you're interested in Sprague Grundy theorem, you can look at this theorem here. Oi. Here. It's not too complex, but I don't want to, to prove it. Okay, thank you for watching. Goodbye. If you have any questions, you can ask me in the chat. I ask you to any question about Sprague theory, about Minimax.